I'm recording this in the morning, so good morning, class. This video is only a supplement for your notes. Make sure you go over the notes. I'm just going to cover the definitions and the graphical interpretation for the graphs, which is very important. In our previous unit, we saw sound waves and their speed, but never really defined what sound was. We just said sound has a speed of this, and then get uh, something else, right? Like the wavelength, etc. And sound is a vibration caused by a vibration. I'm going to say that again to let it sink. Sound is a vibration caused by a vibration, which travels through a medium as a longitudinal wave. We had transverse, standing, and longitudinal waves. And I said an example for a longitudinal wave is sound, okay? The way it works, picture a speaker. Sometimes you can see it vibrate. So those vibrations make the air molecules vibrate, and then we get sound, okay? We had characteristics for the waves such as wavelength, period, nodes, antinodes. We had amplitude and frequency. We're going to revisit those because they relate to sound. Let's start with the frequency. So frequency was the number of oscillations per unit time. And if we take a look at this graph over here, we're going to call this top wave 1 and this bottom one 2. If we take the x-axis as time, the horizontal one, this is 1 unit of time, then we can see wave 2 repeats itself more times than wave 1. Thus, wave 2 has a higher frequency than wave 1. What does that mean in terms of sound? That means wave 2 will have a higher pitch than wave 1. So pitch, you can think of it as the same as frequency. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. I have Ross here, picture of Ross from Friends. He is speaking in a very squeaky voice, and he's saying, I'm fine. I am not gonna imitate him because you're going to bully me. Anyhow, so I'm gonna write it down. Frequency relates to pitch. Now amplitude. Amplitude, we defined it as the distance from the reference point, which is this dotted line, to a crest, or you could also say to a trough or valley. Now, let's compare these two. The amplitude for wave 1 is greater than the amplitude for wave 2. You can see it by the length of the arrows. What does that mean? It means wave 1 has a higher intensity or has a higher volume. It's going to sound louder. So let me write it down over here. Amplitude is related to volume. Now the right term would be sound intensity, so I'm just going to write intensity. Remember, we're all physicists in physics class. So the higher the amplitude, the higher the volume, or the higher the sound intensity. Now let's talk about the range of hearing. As humans, we have a very wide but very defined range of hearing. The lowest frequency we can hear is 20 hertz. The highest frequency we can hear is 20,000 hertz. So, it's a very wide range. And are there frequencies below 20 hertz? Of course, but we cannot hear them. And we call those infrasonic. And then infra has its root in Latin, and it means below. Frequencies below 20 hertz are infrasonic, or sound below 20 hertz is infrasound. Now ultra, again, oh, ultra, there you go. Again from Latin, and that is beyond. So frequencies beyond 20,000 hertz or 20 kilohertz are ultrasonic. And sound beyond 20,000 hertz is called ultrasound. I'm going to write it down. Ultrasound. And yes, this is where the ultrasounds in the medical field come from physics. And we're going to cover this more in depth when we study reflection and refraction. But I just have a picture over here of an ultrasound, or an image, better set. And I thought it was pretty cool how this baby's, doing a peace sign. I thought that's pretty funny. I don't even know if it's true, but who cares? Now the good stuff. The examples. We have an example with two human beings. One has a low-pitched voice, that's a deep voice, and the other one has a high-pitched or squeaky voice. Now let's pay attention to the wave for the low-pitched voice section. It looks longer, way longer than the one on the right. You can see it. The amplitude is small because they're speaking softly, as you can see in the top. Speaking softly, low volume. And for longitudinal wave, we have these areas of compression. We're going to study them and name them correctly later on. But see, these are areas of compression. And the distance from one area of compression to another area of compression is the wavelength, same as from crest to crest. For a high-pitched voice, you can see the areas of compression repeat themselves a lot more frequency, than the low-pitched voice. But the amplitude is the same. I have this red dotted line to help us visualize. They have the same volume. So now let's say they're speaking softly, but they want to speak louder. In theory, they're going to use the same frequency. In theory, okay? Same frequency, but what's going to change is the amplitude. They're going to have the same pitch of their voices, but the amplitude is going to change. It's going to increase because they want to increase the intensity, the volume. Now notice how more well defined the areas of compression are. They're very obvious. Same with the high frequency one. Now the wavelength is still the same, notice. But the areas of compression are way more defined because the sound is more intense, higher volume. Whenever you see a graph and you see high frequency, high pitched, very, if the amplitude is somewhat large, then they're speaking in a high volume. And if the amplitude is small, then very low volume, okay? Low intensity of sound. This is the intro. No math. I know you're sad. Math is our favorite. But don't worry, we'll get to use math next section. Bye, everyone.